Okay, cool. Let's just get started. Welcome everyone to lecture 12. So far we've learned a lot about how, we convert words into vectors, how we convert sentences into vectors, and basically take actions in the real world using that. So like classify documents. We learned about transformers. We learned about pre-training. Today is going to be a little bit different. I'm going to be talking about how you can train large models on GPUs and a few basics about how these ML systems work. And it has nothing to do with natural language at all, but hopefully it's going to be useful for final projects. So I'm going to spend some time on mixed precision training, some time on multi-GPU training with DDP and FSDP, and hopefully by the end of the lecture, these terms will make sense, and some time on parameter-efficient fine-tuning. But before we get into the lecture, just some announcements. Proposal grades are going to be coming out shortly, hopefully by the end of the day. Thank you so much for all the hard work. I know it's kind of getting a little bit crammed with a lot of deadlines for assignment 4 and the project proposal, so thank you so much for all your hard work. The other thing is the project milestone. Details should be out shortly, if not already out on the website. So it's worth 5% of the overall grade. It's due 12 days from now, and it's a maximum of 2 pages. And really, the way to think about the milestone is to use this as a forcing function to get work done for your final project. With that out of the way, let's just jump into the material. So I'm going to start by thinking about how parameters and gradients and generally numbers are represented in computers. And I promise it's going to be relevant to deep learning pretty soon. So let's start with floating point. How many people here are familiar with this cartoon depiction of FP32? Can you just get? Okay, so some of you. So yeah, let's kind of recap how floating points are represented in computers. So firstly, FP32, that's like 32 bytes. So the memory requirement it's 32 bits, so the memory requirement is 4 bytes, okay? And so if you're thinking about neural networks, then for every single neural net parameters, you need 4 bytes of GPU memory. And the way to convert this cartoon into a real number is something like this. So the first bit there is the sign, and then the stuff in green represents the range, and then the stuff in blue represents precision, okay? And so for FP32, there's like, you can represent like a pretty large range, and it's fairly precise, right? And so the larger the stuff in green is, the more numbers you can represent, which means more smaller numbers and also like larger numbers. And the more stuff in green, the more stuff in blue we have, the greater a precision in representing actual numbers, okay? So another popular data type that takes half the memory of FP32 is FP16. And the way we reduce memory is we're going to reduce the stuff in green, so there's going to be less range, less dynamic range, and also the stuff in blue, which means there's going to be less precision, okay? But the good thing is that we can save memory, so we slash memory requirements in half. So let's think of a scenario where you're trying to train a big neural network, and your model parameters and gradients are represented in FP32. You start training, and suddenly you get an out-of-memory CUDA error, okay? And so just based on what we've seen so far, one possible solution is you cast everything into FP16, okay? And if you do that, you reduce memory usage by half. So let's kind of work through what are some possible problems with doing something like that. Like I said, because there's less stuff in green, there's going to be less range. And so that means a lot of very small numbers will get converted to 0. And a lot of really large numbers will get converted into nans, okay? And there's also less precision because you have less bits in blue, which means you're going to get rounding errors. For example, 1.0001 gets converted to 1 in half precision. And I have a little screenshot of how you can test various properties of data types, right? So basically the things to look at are the epsilon. The epsilon is like the smallest number such that if you add that to 1, you don't lose any precision. If you add a number that's smaller than epsilon to 1, that gets just rounded down to 1. And the smallest normal is the smallest number that can be represented in FP16. Anything smaller than that, it goes straight to 0, okay? And for neural network training, if a lot of small numbers get rounded down to 0, that's actually not good. So here's a diagram that I took from an NVIDIA blog post that's just showing just sort of some gradients during the course of training. And more than half of these gradients will literally just get set to 0 in FP16, which is kind of a problem. And that has to do with the range of FP16. And the second problem is with precision, right? So we have basically less precision, and so our updates are not going to be precise, okay? So the solution, here's one possible solution, right? So we're going to use FP16, but we're also going to use FP32, okay? So that's sort of the high level idea. And what we're going to do is we're going to maintain a copy of the model in FP32, and let's call those master weights. And then you get a little bit of data, you run a forward pass, and then when you run your forward pass, you run it by converting from FP32 into FP16, okay? And then you get a gradient, run a backward pass, and then get your gradient in FP16. Okay, so everything so far has happened in FP16. Then you take your gradients, upcast them into FP32, and then update your master weights. And then once you update your master weights, you copy them into the FP16 version of the neural network. Okay? So this seems like a reasonable scheme. You know, I'm using FP16 on my GPU, but I have the full sort of 32-bit precision also lying around somewhere, so I can have more precise updates. Okay? Can someone tell me why this is still problematic? Any guesses? Yeah.
Won't it be like really slow because you have to copy like the 32-bit versions from like GPU into like some disk memory?
Yeah, so that's a good point. So you can often like overlap I/O with like forward and backward passes. So practically this is not a problem. But yeah, that's a good point. Potentially, if your network is very, very small, this could be a problem. Yeah.
Gradients are usually fairly small, like individual gradients are usually fairly small, and when you copy the FP16 computed gradients onto FP32, you may be sending your network somewhere else where you don't want it to be.
So yeah, so that's pretty much the right answer. So let's kind of go back to this diagram that we had. So this shows gradients in the backward pass, and I said that we're going to compute all our gradients in FP16. What's going to happen? Like most of them will just get converted to 0, okay? Which is something that we really would like to avoid. Okay, so here's a possible solution. So what you can do is you get your batch of data, you run your forward pass in FP16. You compute your gradient, but then when you have the, so we're here. So you get a batch of data, you compute a forward pass in FP16, you get your loss, you scale the loss by some large value, okay? Let's say 100, let's say 1,000. And then you compute gradients. And now you just like scale your gradient by a large number. And so everything that we had on the left-hand side of this red line just gets shifted to the right. And hopefully there's less stuff that will get rounded down to 0, okay? And then compute your gradient in FP16, copy it into FP32, and then divide it by the scaling factor, and then you update your master weights, okay? So this will solve both the problems that we talked about, okay? And so this is basically what we call mixed precision training, okay? And it's relatively simple to implement this in PyTorch. All you have to do is you need to instantiate this grad scalar object, and then within the context of like this autocast, you want to run your forward and backward passes, and then scale down your gradient, and then update your model parameters, okay? But then this seems a little complex. We have to deal with sort of scaling the loss and then scaling it back down. What if you multiplied it by 10,000 and that leads to nans? And so then you have to kind of scale, you have to update your scaler. You have to, like, in the next iteration, multiply by 1,000, and you have to kind of adjust to sort of network dynamics, okay? So we'd like to not do gradient scaling. So can we do something better, okay? So the reason why we have to do the scaling is, just recall sort of the role of sort of the bits in green. That kind of tells you what is the dynamic range of the data type. And we needed scaling because FP16 has a much smaller range compared to FP32, right? And so because of that, FP16 cannot represent very small numbers. Okay, so how do we solve this? Any ideas? Yeah, so here's the problem, right? So in FP16, because you have fewer bits for the exponent, you can't represent very small numbers. So if you have something that's smaller than, 6e minus 5, it gets rounded down to 0. And that's because of the dynamic range of FP16. So how do you solve that?
Sacrifice precision, so have more green bits.
Absolutely, yeah. So that's the right answer. So what we're going to do is we're going to sacrifice precision. So that's the idea for B float 16, which stands for brain float 16. So you're going to have exactly the same number of bits for representing the range. So that's going to be 8 bits. So it has the same dynamic range as FP32, but a lot less precision. And it turns out that this is okay for neural network training, okay? And now if you use B float 16, you don't need to use grad scalars anymore. It's as simple as wrapping your model forward pass and backward pass within the right context. The one caveat about B float 16 is that it's not available on all GPUs, so you need to have the latest sort of Ampere NVIDIA architectures, which the H100s, the A100s, the A6000s have. But if you have like a older GPU, then you might not be able to utilize B float 16.
Sorry, can you clarify why having less precision but the same amount of E bits? Yeah, so it's B float 16 and, oh, never mind, sorry. I'm looking for one thing. Thanks. Okay.
So here are some kind of results. So someone fine-tuned Distilbert for sentiment classification on a single A100. At the very top is float 64, which is like, really, really rich 64-bit representation of floating points. It takes about 25 minutes, and you get a pretty high accuracy, but it also takes a lot more memory, okay? And all the way down, we're using mixed precision training with B float 16, and now we have reduced training time by roughly a third. More or less have the same accuracy, a little bit better actually, because there's some regularizing effect from the half precision representation, and then a lot less memory. Okay. And the reason we see speedups for training is because matrix multiplies tend to be faster when you are multiplying in half precision. Okay, so before we move on, are there any questions about this? Okay, cool. So let's keep going, and let's sort of change the setting, right? So now we have more than one GPU. Now we have multiple GPUs, and we want to train a network over all of the multiple GPUs that we have. Okay. So let's start with some basics. Okay. So here's a cartoon showing basically a model and an optimizer receiving some data from a data set, okay? And let's kind of work through what's stored on GPU VRAM, okay? And this is going to be somewhat of a lie, and I will point out what my lie is soon. But just to keep things simple, we have the neural net parameters, okay? So let's say we're doing mixed precision training, and so it's stored in FP16. And then we have an optimizer, okay? And when I first saw this, few years back, I was very surprised to see that optimizers also need memory, but If you're using something like Atom, then you need to store the Atom momentum term and the Atom variance. And every time you get a gradient, you have to update Atom momentum and variance. And that's what you use for updating your parameters. And because you're using mixed precision training, these have to be represented in sort of FP32. Okay. So that's what the picture looks like if you have a single GPU. Now let's say we have multiple GPUs. Okay. And what we'd like to do is first divide our data set into, let's say we have 4 GPUs, right? So we'll divide our data set into 4 parts, and we'll maintain a synchronized copy of the model, and every model receives its own slice of the data set, okay? In the beginning, we have a synchronized model, and everyone has their own copy. We run a forward pass, okay? So this forward pass receives different data points. And so every model is going to have different activations. And correspondingly, every model is going to have different gradients, okay? So you run a backward pass, every model has a different gradient because there's different data points. And then we're going to run a synchronization step. And what synchronization is going to do is communicate gradients between different workers, okay? And so I'm going to introduce the first sort of MPI primitive in this lecture. And that primitive is called the all-reduce operation. What all-reduce does is it takes 4 pieces of information in this example on 4 different GPUs. It sort of merges everything together and then distributes it to all of the GPUs. Okay? And the communication overhead of doing that is 2 bytes per parameter, because remember we have FP16 gradients. Okay, so 2 bytes per gradient, and then this needs to be communicated, and so the overhead is 2 bytes per parameter. Okay, so that's the all-reduce operation. And then once gradients have been communicated, so they have to be communicated by sort of gathering on one worker and just sort of distributing the cumulative gradient. At that point, every optimizer has the full gradient, and then the optimizer can update the model so that you maintain synchronization. Okay, so that's the basic. That's known as distributed data parallel. Okay, that's good, but turns out that it has really poor memory scaling. So let's kind of go through our math for how much memory is needed, right? So we have the model parameters. That's FP16 because we're doing mixed precision training. And then for the gradient, we also have the gradient in FP16, right? So 2 bytes for the gradient. And then we have the stuff in green. The stuff in green is, let's say we're doing Atom. So we need to store the master weights regardless of whether we're doing Atom or not. And then we need to store the momentum and the variance, okay? So that's 12 extra bytes per parameter. Okay, and this needs to be stored on every single GPU, okay? And so the question is, can we do better than this, okay? And so now things are going to get a little bit more tricky, so if you have questions, just stop me, and we can go from there. So the way we're going to improve our memory sort of scaling is via a set of techniques that are together known as ZERO. That stands for Zero Redundancy Optimizer. So this was a set of techniques released by Microsoft as part of their Deep Speed project. Okay? And the idea is going to be that we are going to instead of having every GPU maintain all of this state, so by the state I mean the stuff in blue, the stuff in orange, and the stuff in green, you're going to sort of shard it. Okay? So there's going to be shards so that not every GPU has all of the parameters or all of the gradient, but by communication they can sort of synchronize. Okay, so that's pretty much what the sketch for this is going to look like. Okay, so let's look at stage 1. So like Zero has like multiple stages. So there's stage 1, 2, and 3. In stage 1, we're going to shard the stuff in green. So stuff in green was the optimizer state. And so the way we're going to shard and still maintain synchronization is something like this. Okay, so every GPU has the full set of parameters in FP16, and every GPU has its gradient for its data. Okay, but it only has a sharded copy of the full optimizer state. And the other requirement is that every GPU is responsible for updating the parameters corresponding to its own shard. Okay? So if you go step by step, this is what it looks like. Every GPU has its own data. Every GPU gets a gradient on its subset of the data. Okay? Then we perform reduce scatter. So now this is the second MPI operation of the lecture. So we've done all reduce. This is the second one. This is called reduce scatter. What a reduce scatter does is every GPU has the full gradient on its data. And what you want to do is you want to take the chunk corresponding to, let's say, GPU 1. So let's say you're GPU 0 and you've computed the full gradient for all the parameters, and you want to communicate the chunk for GPU 1 to GPU 1, okay? And same for GPU 2 and 3, okay? So what you're going to do is, from the full gradient, just communicate the bits that a different worker wants to that worker, okay? And every GPU has to do that. So that's called a reduce scatter, okay? And then once every worker gets the gradient corresponding to its shard, they're going to update its parameters, and then once they have updated their shard, they're going to sort of perform an all gather. So what that means is, let's say you have a neural network with just, let's say, 8 parameters, 2 parameters on each GPU. At the end of this, each GPU has updated their subset of parameters, and then they're going to sort of do an all gather to just sort of maintain synchronization. So every GPU gets the full set of parameters that are all updated. Yeah.
Is maintaining this and you're not merging them together sort of in that way. What makes this more efficient?
Sorry, could you repeat your question?
So basically, can you go over why this is better than doing the previous approach?
Right. So what we're going to do is shard the optimizer state.
Right.
So let's say in our running example, we have a neural network with 8 parameters. Okay. Earlier, we needed the optimizer state for all of the 8 parameters. Now, every GPU has to maintain optimizer state for only 2 parameters, okay? So after the reduce scatters are done, you have the full gradient corresponding to just 2 parameters, okay? So the optimizer state is just the gradient for 2 parameters. The model is going to update only 2 parameters using the partial sort of optimizer state.
But you have to have the entire set of parameters to run the forecast. So you'll eventually get the rest of the parameters back.
So you have the entire set of parameters. You have all the stuff in blue, and you have the full gradient for your subset, but you don't have the full optimizer state. So what you can do is you can only update the parameters for the bits of optimizer state you have, okay? So in our running example that I just made up, GPU 0 updates 2 parameters, GPU 1 updates 2 parameters, and so on. Okay, and then they communicate updated parameters to maintain synchronization. Okay. More questions about this? Okay, so let's keep going. So far we have looked at 3 MPI operations. We looked at all gather, we looked at reduce scatter, and we looked at all reduce, okay? So turns out that all reduce is actually equivalent to running a reduce scatter followed by an all gather operation. And just recall that like for DDP, all we had to do was this all reduce operation, and we computed what's the communication overhead of that. And turns out that when you're doing this optimizer state sharding, you have to do exactly the same amount of communication overhead, just because an all reduce is equivalent to a reduce scatter followed by an all gather, okay? And so we basically saved memory for free, okay? So you should just always use this, okay? Because you're gonna get memory savings and you don't have any additional communication overhead, okay? So we are happy, we saved memory. And now, we want to shard even more things, okay? So let's start doing 0 stage 2. And now, along with sharding the stuff in green, which was my optimizer state, I'm also going to shard gradients, okay? And now this is going to be a little bit more complex because we kind of still need the full gradient for the worker's data slice, okay? But each GPU only has enough memory for instantiating the gradient for a small subset of parameters. So how are we going to deal with that? So we are actually never going to instantiate the full gradient vector. And then whenever a GPU gets a gradient in the backward pass, you instantiate a vector sort of temporarily for the parameter for which you just received a gradient, and then compute the gradient, and then just send it to the right worker. And then you destroy the memory that you just created, okay? That's kind of the sketch, and let's kind of go through this step by step. Okay. So we have 4 workers, okay? Each worker performs a backward pass, and the backward pass happens layer by layer, right? So recall the lecture on autodiff. So you have the loss, and then you have this backward pass where layer by layer you compute gradients, okay? So now let's say you're at layer J. You take the upstream gradient, you compute gradient for the parameters at layer J, okay? Immediately, the moment you compute those gradients, send it to the right worker, okay? So there exists some worker that is responsible for layer J, okay? And what's going to happen is every GPU that's just computed the gradient for layer J for its data slice sends it to the right worker, okay? And then the moment you've done that, you deallocate this memory that you just created, okay? And so this is kind of a fourth MPI operation, but really not very different from a reduce scatter. This is just a reduce. So there are 4 GPUs that have a gradient, and then they just have to communicate it to whoever is responsible for maintaining gradient for that layer, okay? And then, yeah, so there exists some worker that is responsible for a given layer. They're going to update its parameter shard using the full gradient that it received via this communication along with the optimizer state, okay? And then at the end, to synchronize everything, you have to perform an all gather as before. Okay. Any questions about this like high level sketch? Okay. So let's keep moving. Okay. So recall that for 0 stage 1, it was basically free because turns out that an all reduce is equivalent to a reduce scatter plus an all gather. And we're kind of doing the same thing here. We have a reduce followed by an all gather. So this is practically also for free. Okay, so we've gotten away with saving memory without any communication overhead compared to DDP so far. Okay, so let's keep going. Let's try and see if we can shard even more things. Okay. And I think someone sort of alluded to this in the audience early on. So what happens if you shard even your model parameters, okay? So let's say you run into a situation where, forget about the optimizer state, even your model wouldn't fit on a single GPU. And so in that case, what you do is you split up your model. So you split up your model across all the different GPUs. So you shard your model parameters, which is the stuff in blue. But the caveat is that now we're not going to get this for free. We're not going to get memory savings for free. There's going to be some communication overhead, okay? And this is 0 stage 3. This is the final stage of 0. This is also known as FSDP, fully sharded data parallel, for anyone who's heard that term before. And here's sort of the high-level sketch, okay? And I feel like this is kind of the easiest to understand compared to 0 stage 1 and 2, just because there needs to be communication at every step of the way, right? You can't get away without communicating. So the first thing we're going to do is we're going to take our model and we're going to convert the entire model into FSDP units, okay? So here's a sketch, a simple deep neural network. I'm going to convert that into multiple FSDP units, 3 FSDP units here. Okay, so that's just a data structure, an FSDP unit, okay? We've not done anything so far. And then I have this FSDP unit. I'm going to convert this into another data structure called a flat parameter. And then I'm going to assign a subset of these parameters to every single GPU, okay? So here we have 16 GPUs and a flat parameter consisting of 14 parameters plus some extra padding so that things divide properly. And I'm going to assign each parameter to a distinct GPU, okay? And so that's basically just a complex way of saying that we created some data structures and we just like divided up model parameters to every GPU. Okay, so every GPU gets a subset of model parameters. Okay, now let's start thinking about what my forward pass will look like. So there's no GPU that has the full set of parameters. Okay, so you're running a forward pass. Let's say you're at layer 4. Now, there's no GPU that has all of layer 4, so you have to communicate. So we need to do an all gather operation. That's the operation that we did to accumulate multiple things that are on multiple GPUs so that every GPU has the full thing. So you perform an all gather so that you have all pieces of layer 4. You run a forward pass, okay, and now you don't need layer 4. So you now discard your parameter shards, okay? And now you have to run your backward pass, right? So you computed your loss, and now you have to do a backward pass. Again, let's say you're back at layer 4, you have your upstream gradient, you don't have layer 4, so you need to do another all gather, so you get all the parameters of layer 4. And then you run a backward pass for layer 4, so you compute the gradient for your subset of parameters. So recall that every GPU has different data points, right? So there's going to be different gradients for every GPU, okay? So then for layer 4, you do an all gather, get all parameters, compute a gradient. Every GPU has different gradients. And then you have to do a reduce scatter so that you can send the full gradient to the GPU that's responsible for whatever parts of layer 4 that you're sending, okay? So yeah, so that's basically full FSDP. And then once you sort of run the forward and backward pass, then each GPU will update its own parameter shard using the full gradient that it received just now. And then you do a synchronization, right? So let's kind of do a quick review of everything we've looked at so far. So there was DDP. Which was you don't shard anything, you have the full model, the full gradient, the full optimizer state on every single GPU, and all you're going to divide up is the full data set, right? So you have a big data set of 1,000 examples, every GPU gets 250 examples, okay? And then you compute a forward pass and a backward pass, every GPU has a different gradient, you need to communicate that gradient, and then you synchronize, okay? And so that was called an all reduce operation in MPI terms. And then we looked at 0, which is, now we want to save some memory. We don't want the full sort of memory requirements of models, gradients, and optimizer state on every single GPU. And in 0 stage 1, we sharded the optimizer state so that there's, so that you don't have to maintain the full optimizer state for every GPU. You kind of break that down between all the different GPUs that you have. And we saw that the communication overhead of maintaining synchronization in 0 stage 1 boiled down to basically just doing an all reduce through this identity that says that an all reduce is a reduce scatter plus an all gather, okay? And we save memory for free with 0 stage 1 and 2. So you should just do it, And then with 0 stage 3, things got a little bit more complex because you have to divide up your model parameters, the optimizer state, and the gradient. And so while you're running your forward pass, you kind of have to do some communication to get the full parameters for any layer, for layer 4 in our example. And then also have to do an all gather in the backward pass so you get the full gradient. And then you have to do a reduce scatter so that you can send the full gradient for whatever chunk of the parameter to the right GPU. And overall, that's like 2 all gathers plus a reduce scatter. So that's a lot more overhead than stages 1 and 2. But if you don't have enough GPU VRAM so that you can even load your model onto a GPU, then this is kind of what you have to do. All All right. Any questions about MPI primitives or stages of 0 or FSDP? Okay, cool. So I'm going to fix the lie that I said earlier about the GPU VRAM calculation. So I said that there's just like model parameters and gradients and the optimizer state, but there is this thing, there's this like final thing, the model activation. So like, we've all seen that as you keep, you want to increase the batch size, and there's a point when the GPU says that it can't fit more stuff. And that's because you also need to store model activations in the backward pass, right? And that scales linearly with the batch size. Okay, so the larger the batch size, the more the number of model activations that need to be stored. And by the way, if you're doing mixed precision, this is in FP16 or BF16, but it scales with the batch size, okay? And so that's sort of the other thing that you have to think about. And none of the techniques that we've looked at so far help with kind of sharding model activations. So we looked at a bunch of like basics of like multi-GPU training and like floating point, but it kind of boils down to this very simple flowchart which you can use for your final projects when you're fine-tuning models. So the first thing is always use mixed precision training. You barely ever see a hit in performance. By performance, I mean like a generalization or like F1 or accuracy. And if you're using the newer Ampere architectures, the H100s or the A100s or the A6000s, always use bfloat16. It's just better. And you can check that with that torch command. Okay, so always use mixed precision training. Now, ask yourself this question. Does batch size 1 fit on a single GPU? Okay? If it fits, then try a larger batch size. Okay? Batch size 1 is too small. Try a larger batch size. And or use 0 stage 2. Okay? 0 stage 2 is for free. Just use a 0 stage 2 and increase your batch size. If you can't fit even batch size 1, then you have to see if 0 stage 3 fixes your out-of-memory issues, because now you're going to shard your model parameters. Okay? And all of this is in the context of full fine-tuning, right? So I'm fine-tuning all of my model parameters. Okay. Sometimes the answer to that question is also no. So you can't full fine-tune your model on 4 whatever A100s or A6000s. And you've tried 0 stage 3, you've tried mixed precision training, you have a batch size of 1, maybe you did gradient checkpointing, activation checkpointing, and nothing works. And so now, basically you can't do full fine-tuning. And so the thing to do is to try parameter efficient fine-tuning, okay? And that's going to give you a lot more memory savings, okay? So let's talk about parameter efficient fine-tuning, okay? Why is it called parameter efficient fine-tuning? So in full fine-tuning, you run a forward pass and a backward pass, and you update every single model parameter. And in parameter efficient fine-tuning, you're only going to update a small subset of the full set of parameters, okay? And why would you want to do that? So, maybe you're in a setting where you cannot full fine-tune even with batch size 1. You've tried all the tricks possible. It just wouldn't fit. And so maybe you have to do parameter efficient fine-tuning. Maybe the other possible reason why you want to do it is kind of slightly more scientific. These like models these days are heavily over-parameterized, and you have a small data set, and you believe that if you do parameter efficient fine-tuning, then you can get a better like generalization, okay? Or you believe that it's going to match full fine-tuning, okay? Sort of a second reason for wanting to do efficient adaptation. The plot on the right here shows in red, it's sort of the estimated growth in training compute for training the largest AI models. And the line in blue is the global compute capacity. So very soon we are going to overshoot the global compute capacity and going to need a lot more compute than the global capacity. And so this is kind of not sustainable. And there are arguments to be made about how if we keep going down this route, then AI development becomes concentrated in only the hands of a few well-funded organizations, and as students we can't do it. And so that's a problem. And then also, like, if there's only a small number of players that are training and fine-tuning models, then they may bias the model in specific ways that reflect their value systems and not sort of the broader public. And so that's another reason to do to think about efficient adaptation. And there's sort of this paradigm in machine learning in general and NLP specifically to focus a lot on accuracy instead of efficiency. And so the plot on the right here shows the percentage of papers where the main contribution is a method that produces just more accurate models versus methods that produce same accuracy for more efficiency. And so we can see that for most conferences, the vast majority of papers are about accuracy. And there's very few papers about efficiency, okay? And so maybe this is kind of leading to this like monoculture, and maybe that's why we want to focus on efficiency. The second, maybe bigger sort of concern is that there's this huge hidden environmental cost of training and fine-tuning large language models. So I was just reading some report where they said that the cost of training GPT-3 was equivalent to 1.1 million tons of carbon emission or some such number, and they kind of estimated that that's the cost of running a coal power plant for 10 hours straight, okay? All right, and for an example closer to home, in the reinforcement learning class, there was like, the final project, not the final project, a homework assignment, and a lot of students implemented kind of a common algorithm. One or two algorithms that sort of outperformed everything else, but it used a lot more power, okay? And someone did this calculation that if everyone had used the most efficient algorithm, that would have, if everyone had used the more efficient algorithm, that would have reduced the power consumption of the class by about 880 kilowatt hours, which is what an American household uses in a month. Okay, so there's another, like, these are all reasons to think about like efficiency and like how you can like fine tune your models with like less resources. Okay, so let's kind of jump back into like parameter efficient fine tuning. Okay, and let's start by recapping what full fine tuning is. Any questions so far about any of this? Okay. So let's recap full fine-tuning. So let's say we have some large pre-trained autoregressive language model. Let's say it's a GPT. And maybe we want to use it for summarization. Maybe we want it for semantic parsing, so like converting natural language to SQL commands. Or maybe we want it to answer questions about paragraphs, okay? And what do? We collect a data set of XY pairs. And then we do full fine-tuning. In full fine-tuning, we are going to update all of the model parameters based on the gradient for some loss function, okay? And maybe that's not feasible. GPT-3 has 175 billion parameters, and so there's just like a lot more parameters to learn. And even once you have done full fine-tuning, you kind of have to store all of the parameters. And if you're doing like several tasks, you have to store parameters for every task, okay? So can we do better? Okay. So the main idea is instead of updating all of the parameters, I am going to update a much smaller number of parameters, okay? And then instead of finding sort of a delta theta, which is the same size as the entire set of parameters, I have to search over a much smaller space. And then the added benefit is I can store this much smaller delta pretty easily on disk. And hopefully it's going to require less compute, and hopefully it's going to generalize almost as well as full fine-tuning. Okay? So there's many different ways of kind of operationalizing this high-level idea of parameter-efficient fine-tuning. The one I'm going to talk about today is LoRA. Okay? So that stands for low rank adaptation. And that basically comes from this observation that when you have big language models that you fine-tune, oftentimes when you look at sort of the like geometric structure of the gradients, they tend to have a low intrinsic rank. Okay? Do people remember rank and SVD? All right. Okay. So, so these parameters, so the gradients tend to have a low intrinsic rank. Okay. And so what the authors realized is instead of fine-tuning the entire set of parameters, you could instead fine-tune a much smaller, let's say, rank R matrix for every full rank matrix that exists in the model. Okay. So let's say we have some pre-trained weight matrix W naught. And what I'm going to do is instead of applying some kind of arbitrary update, I'm going to make sure that the update has this following form. Okay? So it's going to be the product of two low rank matrices, B and A. Okay? So A is in R, is an R cross K matrix, and B is a D cross R matrix. Okay? And R is the rank. It's much smaller than either the sort of incoming dimension and much smaller than the outgoing dimension. Okay? And the term alpha, you can think of that as some kind of trade-off between the knowledge that's already stored in the pre-trained model versus some additional knowledge that you want to add into the model. Okay? So if alpha is 0, then you're not doing anything. If alpha is something really small, then you don't really want to change your model parameters all that much, and you want to add some really small task-specific knowledge. And then additionally, the only trainable parameters here are going to be A and B. Okay? Okay. And then sort of the other thing to note about this is since I'm representing updates as this product B times A, as I increase R, that's going to converge towards full fine-tuning, right? So you kind of have the slider that you can use to control how much fine-tuning you want to do, essentially. And then the other important thing is inference latency. So what you can do is you can just store these learned matrices for every task, and whenever you switch to a different task, you can just remove the extra term that you've added to every matrix for that task and add in sort of the task-specific terms for the new task that you want to run inference on. Okay, and the cost of like storing these like much smaller matrices is also way lower than storing sort of the full delta. Okay. And we'll kind of see where you should apply LoRA, but like generally you want to apply it to the weight matrices in self-attention. Okay, so in code it actually looks fairly simple. So what you're going to do is when you're running the regular forward pass, then you sort of just like compute the hidden state as, let's say, the product of the matrix and the incoming feature vector. Now with LoRA, what you're going to do is you're going to freeze your model parameters. You're going to compute the H as before. And then to that, you're going to add this additional offset term. And that's the only thing that's going to be trainable. Okay? And that's pretty much all you have to do. We have to do it for every single like weight matrix for every single layer. Okay? But yeah.
So there's like an alpha term in the second to last line. Where do you define alpha in the rest of it? Or do you just like put it somewhere?
So you define this somewhere. if you set it to 1, that's like saying that I kind of want like an equal trade-off between pre-trained knowledge and the new task-specific knowledge. Typically, people set it to 1. You could set it to something larger than 1 if you believe your task is something that the model, the pre-trained model has no idea about, or something smaller than 1 if you don't want to change the model too much. So that's basically LoRA. In practice, so I said there's a bunch of different parameter-efficient fine-tuning methods, right? So I'm not even going to name all of these. There's adapters. Some of you might have heard about adapters. There is bitfit, which is not here. And so there's like lots of different, like p-tuning. But it turns out that like compared to a lot of these different methods, it's kind of like pretty high performing on a bunch of different tasks for these like relatively smaller models. Okay, and then if we try and look at some of the bigger, like we're trying to fine tune some of the bigger models like GPT-3, and then compare it with other parameter efficient fine tuning methods. So full fine tuning is at the very top. Then we have bitfit, which is you only fine tune the bias terms, and adapters. Compared to that, firstly, LoRA requires a lot fewer additional parameters that you need to store, and it kind of gives you a good trade-off for accuracy compared to full fine tuning. And sometimes there's a regularizing effect from fine tuning only a small subset of your model parameters. Okay. So, the question is like for every matrix, you can apply LoRA. And I said that you want to apply it to the various learned weight matrices inside self-attention. The question is what parameters you want to apply LoRA to. And generally, the rule of the thumb is that if you apply it to the matrix that takes your hidden state and converts that into queries, and the matrix that converts your hidden state into values, apply LoRA to those, and that's pretty much going to give you the best performance overall. The other hyperparameter for LoRA is the optimal rank. So recall that these like two matrices, B and A, that are both like low rank. And turns out that like already with a really small rank, you can get a pretty high performance. Okay, and this is much, much smaller than sort of the hidden state dimensions of most of the matrices for most models these days. Okay. All right. So we covered a bunch of things. We talked about floating points and mixed precision training, multi-GPU training, DDP, FSDP, LoRA. Kind of boils down to a very simple flowchart that you can just like use for your project. So if you were sleeping through the entire lecture, maybe now's the time to wake up and just like look at this flowchart. So always use mixed precision training. Okay, if you have the newer Ampere architectures, use bfloat 16. Try with a batch size 1. Okay, if batch size 1 fits, try a larger batch size, and then always just use 0 stage 2. Okay. Batch size 1 doesn't fit, try 0 stage 3. Maybe try gradient checkpointing, activation checkpointing. Sorry, there's a question.
This is assuming we have more than one GPU, right? Because otherwise 0 stage 2 doesn't really help us much.
Oh yeah. So all of this applies only if you have more than one GPU. Yeah. If you have a single GPU, yeah, you have to do other things. Maybe have to like heavily quantize the model. And even then, I don't think you can fine-tune some of the bigger models. Yeah. So assuming you have multiple GPUs, you can try 0 stage 3 if you have out-of-memory errors with a batch size of 1. And if that doesn't work, you can try LoRA. Okay. And the main hyperparameters in LoRA are the alpha, the rank, and what weight matrices to apply LoRA to. Apply that to the query matrix, apply that to the value matrix, set rank to 8. Okay, that's a good starting point, set alpha to 1. Okay, just do that and you should be good to go. Okay, so you can fine tune your models and things should be reasonably good. Okay, so I'm going to end now unless there's questions. Oh, there's one question in the back.
Yeah, there was this diagram in one of the slides. I was wondering if you could just like go back to it and like walk through it a little bit on on slide 48. Yeah, this diagram on the left.
Right. Okay. So let's go through this diagram. So basically, what this diagram shows is how the communication overhead is really not that bad if you have a fairly big model, such that the time it takes to do a forward pass, you can already sort of prefetch all of the parameters for the next layer. Okay, so that's pretty much the idea. So that's kind of like a standard idea I guess everyone should already be using. Like you want to make sure, and PyTorch does this by default, by the way. Like you want to make sure that you sort of fully saturate your GPU, and then sort of make sure that you kind of overlay that with any additional compute you're doing. And that's pretty much what's going on here. But let's sort of go through this kind of step by step, okay? And so the starting point here is FSDP units. So 0, 1, and 2 are different FSDP units, okay? So what you start by doing is you want to run a forward pass on the first layer, but you don't have the first layer, okay? So let's say you are GPU-K, you don't have the first layer, so you have to do an all gather to get all of the parameters for the first layer. So that's AG0. Okay, at the end of AG0, every GPU has the full set of parameters for the layers corresponding to FSDP unit 0. Let's just say that's layer 1, okay? Or let's just say that's layer 0, okay? So you have the full parameters for layer 0, you run a forward pass. So that's the stuff in blue. And while you're running a forward pass through the first layer, you're going to be smart about communication overheads, and while you're running that, you're going to prefetch the parameters for the next FSDP unit. Okay, so let's say layer 2 is a different FSDP unit. So that's AG1, okay? And so you can see that there is like a little bit of overlap between forward 0 and AG1, okay? At the end of getting all of the parameters for layer 1, you're going to do a forward pass, okay? And so on. And then you're going to do AG2. And at the same time, now let's say you just have way too many parameters on your GPU. Okay, so you're going to do a little bit of like memory free. You're going to free up some memory. Okay, so that's the stuff in yellow. Okay, and so that's how that goes. So you basically overlay all gather operations with the forward pass. Okay. And that's how you run the forward pass. Okay, so the communication overhead is really not that bad if you have like a really big deep neural network, and assuming that you have kind of sharded everything properly. Okay, and then you start the backward pass. So in the backward pass, I guess it's a little bit tricky because you want to do these all gather operations to get the full gradient. So let's say it's a 10-layer neural network, okay? So you want to compute the full gradient at layer 10. You need to do an all-gather operation to get all of the gradients, to get all of the parameters at layer 10. And then you have to do a reduced scatter, okay? So you have 4 GPUs. Everyone has the full set of parameters at layer 10. They have different gradients. And so they have to kind of merge their gradients and then sort of split them up to the right GPU. And so that's the reduced scatter. But that's not too bad because you can still like overlay reduce scatter operations with the backward pass, okay? And so that's what you see happening on the backward pass there, okay? And then like along with these forward and backward passes, at sort of regular intervals, you have to make sure that you kind of free up GPU memory. So for example, once you have run a forward pass through layer 1, now you're on to layer 2, you don't need anything in layer 1, so you just like free up the memory in layer 1, okay? That's pretty much the idea behind this diagram. So there's a few details here. One of the details is like in FSDP, unit 0 is sort of treated differently. So you'll see that unit 0 is never freed up. That's just sort of an implementation detail in FSDP. I'll just quickly say one more thing about FSDP and take a question, okay? So the presentation here makes it seem like it's so simple and that it can be applied to any neural network, right? But turns out that that's not the full picture. So you need to do this kind of, like you need to kind of divide up your neural network into FSDP units, okay? And depending on how you, depending on what policy you use for dividing up your parameters into FSDP units, there's different communication overheads, okay? So for example, it makes sense to kind of have like multiple like consecutive layers in the same FSDP unit and so on. And so this is like very architecture specific. So when you start to use this in PyTorch, you'll see that the FSDP wrapper requires sort of a sharding policy. And that is like very architecture specific. So because everyone uses transformers now, they're like very sort of handcrafted, fine-tuned policies for transformer, like for creating FSDP units and sharding strategies for transformers. But let's say you want to, for your final project, you came up with a new architecture, subquadratic attention, whatever. Maybe it's not going to be as efficient just because you don't have the right sharding policy, okay? So that's like one detail about FSDP that maybe you want to keep in mind. Okay, you had a question?
Just a clarification. You mentioned you can throw away the weights that you don't need after each layer of forward pass, but then when you compute backward pass, do you stream them back in each time? Or do you sort of cache some or cache resend, or is there any caching going on, or do you throw them all away and stream them all back?
So there might be some caching, but in the system, but the idea is that you just sort of throw them away, or at least to the user, it seems like you've thrown it all away in terms of like GPU RAM utilization.
And then we stream them each layer again. Got it.
And so that's why it's important to like shard it properly, right? So for example, if like every consecutive layer is like sharded such that it's on multiple GPUs, then you kind of always are communicating, right? As opposed to, you kind of did like all gather, and then all of the sort of next 3 layers are loaded in. Okay, so that's why like, how you shard and this like sharding policy becomes important. Okay. Okay, so if there's no more questions, let's end early. Thank you so much.